Digital signature systems are systems where the state of information and data is captured in, and now take that, digital signatures. These digital signatures are calculated not based on symmetric keys, as it was the case with message authentication codes, but digital signatures are calculated based on the private key of a participant in such a system. Once such a digital signature for a plaintext is created based on the private key of the participant, then this digital signature can be verified with the corresponding public key, which verifies that the digital signature matches the plaintext and that the digital signature was created with the private key. Let's have a look at the flowchart on the left, which describes how such digital signature schemes really work. Also, let's assume it's Alice that wants to be able to digitally sign data, and that Alice, for that purpose, owns a public-private key pair for the purpose of creating and verifying digital signature, and that she has made the corresponding public key publicly available. Alice then, once she has a plaintext that she wants to digitally sign, takes her private digital signature creation key and the plaintext and triggers a signing process from which she gets a digital signature out of. Alice can then release the plaintext together with the signature. Anyone receiving this plaintext and signature can now verify that the plaintext is really the plaintext that Alice created by taking the public digital signature verification key of Alice and triggering a digital signature verification process, which will indicate whether the digital signature for this plaintext was really created by the private key corresponding to the public key of Alice. The difference to message authentication codes, which provide authenticity to information and data, is now that these digital signatures now allow anyone, and not just a recipient within a certain session of communication, but anyone with access to the public key of Alice, to conclude that the digital signature on a plaintext is a digital signature that was created with the private key of Alice, and that the plaintext is still exactly the plaintext that Alice was sending. The question we have left to answer is, how do these digital signature creation and verification processes now really work? The creation of digital signatures is a construction based on cryptographic hash functions and based on asymmetric encryption. To understand this, let's have a look at the flowchart on the left. We know that digital signatures are created for a plaintext and under a certain private digital signature creation key, so we can see that the digital signature creation process takes a plaintext and an asymmetric private key as an input. The first step in the creation of a digital signature is to hash the plaintext with an underlying cryptographic hash function. This results in a hash of the plaintext that was provided as an input. This hash value of the provided input plaintext is then simply asymmetrically encrypted with the private key, with this asymmetrically encrypted hash value then being the digital signature. That's it. The security of such digital signatures now relies on the underlying hash function to be a secure cryptographic hash function and on the security of the asymmetric encryption scheme used to asymmetrically encrypt the hash values of the plaintext. Knowing that digital signatures are asymmetrically encrypted hash values of the associated plaintexts, the verification of digital signatures is then a process taking the digital signatures, the associated plaintext, and the asymmetric public digital signature verification key as an input. In a first step, the digital signature received is asymmetrically decrypted with the public key, which results at this point in just some hash value. Then, in a second step, the associated plaintext is hashed, which results in a hash value of the plaintext. And in a third step, this self-calculated hash value is compared with the hash value that was obtained from the asymmetric decryption of the digital signature, and if these two hash values are the same, the digital signature is successfully verified. If either the digital signature is wrong, or the plaintext was changed, or the wrong public key was used, the digital signature verification mechanism will fail. There are a couple of different types of digital signature systems. One key type of digital signature systems is the one we just had a look at, and that relies on the asymmetric encryption of hash values. This asymmetric encryption takes place with RSA, and the current recommendation is to use the probabilistic RSA digital signature scheme RSA-PSS, which introduces randomness into the creation of the digital signatures, which is required to really provide the security to digital signatures created. Another key type of digital signatures is digital signatures following the digital signature algorithm, DSA, which results in digital signatures not based on RSA, but based on the discrete logarithm problem. DSA has been a NIST standard since 1991, but has a strong requirement on a very high quality source of randomness, which may prove challenging or even impossible for systems to provide, and as such, DSA is likely soon delisted as an approved digital signature scheme. An elliptic curve variation of DSA-based digital signatures are elliptic curve digital signature algorithm digital signatures, which enjoy some speed and key length gains over DSA, but essentially have the same security challenge like DSA digital signatures, and as such are likely soon delisted as an approved digital signature scheme as well. In order to not have the security challenge around high quality randomness, the by now highly popular EdDSA type of deterministic digital signatures has been developed, which are elliptic curve digital signatures, and with the two most popular implementations now being Ed25519 or Ed448.